So we left off last class talking about the remainder theorem, the factor theorem, the idea that a polynomial function, whatever the degree is the maximum number of zeros it can have, and we talked about possible rational zeros. So we're going to apply all of this now to if we wanted to solve an equation, specifically in this case a cubic polynomial, and find all of the real zeros given no zeros to start with. Okay, so the notes kind of guide us through this, and you're always going to go through this same routine. So you're going to first list how many possible real roots this can have. Well, remember we talked about how the degree tells you the maximum number of zeros this can have. So this can either have 3 real zeros, or if it has some imaginary zeros, we know that they have to come in pairs, so it could also have 1. It's not going to be possible for it to have no real zeros, so it has to have at least 1. Okay, so now we can write a list of the possible rational zeros. And remember, that's a ratio or a fraction of factors of the constant, which in this case is 20. So factors of 20 over factors of the leading coefficient. In this case, the factors of the leading coefficient, that's 1. So plus or minus factors of 20, and I list my factors by starting small and writing its partner later. 2 goes into it. I'm probably going to run out of space here. 10 is its partner, and then 4 and 5. I did run out of space. Okay. And then factors of 1, there's only 1. And then we pair them up. Well, in this case, there's only one possible combination we can make here, but plus or minus 1, that's 1 over 1, 2 over 1, 4 over 1, 5 over 1, 10 over 1, and 20 over 1. So these are all the possible rational zeros. Does that mean that they're all zeros? No, there's only going to be 3 or 1 real zeros. But these are all the possibilities. And we want to now test one of those possible rational zeros in this equation. And the easiest way to test these is to use synthetic division and see if you get 0. Because remember, according to the remainder theorem, if you get 0, then you know that what you were just testing must be a 0. And if you wrote it as a factor, it would be a factor of the polynomial. So a good trick to try is to first add up the coefficients of this polynomial. So 1 plus 8 plus 11 minus 20. And if you add those up, signs and all, and you get 0, then you know that 1 is going to be a 0. So this is kind of an easy way to decide, okay, I'm going to test 1. And a lot of times you will be working with these polynomials where the coefficients add to 0, so you should try to test 1. So I'm going to do synthetic division plugging in 1. So I put my coefficients. I don't need any placeholders because I have every term. If you wanted to, like I was doing in class, 3, 2, 1, 0, that's the constant. Make sure that you got every term. Okay, so we always bring down the first term, 1, multiply it by the number out here. So times 1, add these, multiply by 1, add these, multiply by 1, and add these. And if you get 0, then you're in business. You know that you have that number that you tested, in this case 1, x equals 1 is a 0. Okay, so what you got on the bottom row of your synthetic division problem gives you your coefficients for your depressed polynomial. And when I say depressed polynomial, I mean your polynomial that is 1 power lower than this polynomial that you started with. So since we started with a cubic polynomial, and we were technically dividing it by a factor with x involved, x cubed divided by x would be x squared. So these are the coefficients 1, 9, and 20 for the new polynomial that's 1 power lower than the original. So 20 will be the constant now. 0 that we got at the end, that was just our remainder that told us that 1 was a 0. So now we're working with this. And part D says to write that 0 as a factor, so you want to write 1 as a factor, that would be x minus 1, along with the depressed polynomial, x squared plus 9x plus 20. And then you can factor that depressed polynomial. So think back to Algebra 2, and really we've been factoring a little bit this year. You're looking for numbers that multiply to give 20 and add to give 9. So that would have to be 4 and 5. They'd both be positive. Okay? So that's what you're doing in part D, factoring your depressed polynomial. That's basically your answer that you got on the bottom row of your synthetic division. And then the last step is to solve this thing. Well, we've got a bunch of factors, and if we set these equal to 0, we can solve each factor. Well, we already know that 1 is a 0 because that's what we tested when we did synthetic division in part C. And now we also know that negative 4 is a 0 and that negative 5 is a 0. So it turns out we have 3 real zeros. And if we wanted to sketch this polynomial, we could also do that. So I know because it's positive odd, its end behavior is going to be going down on the left and up on the right. Here's negative 5, here's 1. So my zeros are 1, negative 4, and negative 5. And I know I'm going to cross every 0 because they each have a multiplicity of 1. So something like this. That's a little bit ugly. There. Now it passes the vertical line test at least. If you wanted to, you could also plug in a number maybe on this region between negative 4 and 1. You could definitely plug in 0 and get the y-intercept. So you could do f of 0, and that would be negative 20. So my graph was not very accurate. It should actually be more like down here. You could even plug in f of negative 2. You can either do synthetic substitution or synthetic division. And what you get if you plugged in negative 2, what you get here, remember, if your remainder isn't 0, it's just your function value. And if your remainder is 0, that's also your function value. So you could also plug in negative 2. In the notes, I'm not asking you guys to sketch this, but just, to start thinking about what you would do, you had to do that on the first homework. Okay, so let's look at this second example. This time we've got a quartic polynomial. The highest power is 4. That's the degree of the polynomial. And to consider how many possible real roots there are, you need to be looking at the degree. So, at most, there's going to be 4 zeros. But there may not be 4 real zeros. There could be 2 real zeros, and there could even be 0 real zeros. So I'll give you a visual of what that would look like. So if you have 4 real zeros, and some of them may be double roots, but I'll just give you an example where you have 4 different zeros. So there's your 4 real zeros. Okay? If we have 2 real zeros, it's going to cross the x-axis twice, and then not cross it twice. And if you have no real zeros, you still have this W shape, but you never cross the x-axis. So if you've got real zeros, it's going to be crossing the x-axis. Okay, so now we want to use the rational zero theorem to write the possible rational zeros. That's going to be plus or minus, and we'll list the factors of 9, that's the constant, so it's always factors of the constant, over factors of the leading coefficient, which in this case is 1. So factors of 9 are 1, its partner is 9, and 3. And 3, I don't need to write 3 twice. If it's its own partner, I just need to list it once, and then the factors of 1 are 1. So my possible rational zeros are 1, 3, and 9, plus or minus any of those. So technically I've got 3 numbers here, but I've got 6 possibilities. I just put it in brackets as kind of a shorthand, but they're all plus or minus. Okay, so now we want to use synthetic division. I give you the option of using long division, but most of you are probably not going to go that route. You are allowed to, though. It works just the same way. And you want to test possible rational zeros. And remember, if you get 0 at the end, then you know that that's a 0. So that trick that I mentioned earlier, we can try and add up these numbers, and if we get 0, then we know that we should test 1. So we add up the coefficients, 1 minus 2 plus 10 minus 18 plus 9. Okay, so does that give me 0? Yes, it does. So 1 must be a factor. So I want to set up my synthetic division using my coefficients, 1, -2, 10, -18, and 9. And I want to make sure that I don't need any placeholders. So 4, 3, 2, 1, 0. Okay, I'm good. I don't need any placeholders. So, and I'm going to do 1 because that should work. I'll switch colors here so you can see what I'm doing. Always bring down that first number. Multiply, add, multiply, add, multiply, add, multiply, add, and you get 0. That's good. So your remainder is 0. You know that this number, 1, must be a factor. Okay, so this problem is a little bit different from the last one. What we get as our depressed polynomial, that's that, these give you the coefficients for your depressed polynomial, which is 1 power lower than your original. So your original polynomial was to the 4th. So now we're working with to the 3rd. Okay? And the next step says to write the 0 that you just got as a factor. So 1 works, so I'll write that as a factor. So this x minus 1 is 1 as a factor. And then I want to write the depressed polynomial along with it. So this, so far, what we have here, this whole line of things, is x to the 4th minus 2x cubed plus 10x squared minus 18x plus 9. That was our original polynomial. This is now it somewhat factored. Okay? So you have two options at this point. You can either keep going with this and do synthetic division again, testing another one of those possible rational zeros. And I think there's a problem in the homework where you have to do that. But if you guys also notice, whenever you have 4 terms, you can also factor by grouping. And this, you can factor by grouping. Sometimes you can't. But if you can, it's pretty easy to do that rather than do synthetic division again. So here you take out a GCF out of the first set of numbers, and you take out a GCF out of the second set of numbers. Okay, and your leftovers, these should match. Your x minus 1s should match. And I know we reviewed this earlier this year, so this isn't really new to you guys. And you take what you factored out and you group those together. So the x squared and the 9 are going to be grouped together, and we write the leftovers one time. And I'm going to go ahead and bring this down as well, x minus 1, because that was a factor too. So this is my original polynomial completely factored. And I want to make sure, if you wanted to, you could check that it's factored by counting up the x's that you have. You should have 4 altogether because this was x to the 4th originally. Okay, so then the last step says to solve it over real numbers. Well, let's just talk about what this would be, because I know we talked about this in class. X squared, if I went to solve this, I had it set equal to 0. I'd get x equals plus or minus, because when I square root it, it's a plus or minus, 3i. I'm just going to write that down here just so that you guys can see this here, x squared plus 9, that factor gave us 2 imaginary zeros. And then these other factors, that gives us x equals 1 and x equals 1. What's the deal with that? I wrote that twice. Well, we talked about multiplicity last class, so x equals 1 is a double root. That might have been what your teacher called it last year, or fancier term, multiplicity of 2. If I was asking you for the multiplicity, that's what you would say. And that tells us that it's going to bounce off the x-axis. It will touch it, but not cross it.